Hello. Welcome, 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 everyone, to 60 Minutes in Space. How many of you, it's your first time coming to this program? Woo! How many of you, it's your first time in the museum? Anybody? Anybody? Yeah, woo!
Woohoo.
We love a woo. Just a little bit of housekeeping for me. First and foremost, I'll introduce myself. My name is Austin Terrell. I'm the Adult Programs Coordinator. I use he, him pronouns. And I am so happy that you are here with us this evening. If you are sitting on the edge or on either end of the aisle, we have some late arrivals. If you want to scooch in, let them in. We would love that. Otherwise, we usually have folks streaming in from the park. Anyways. I'm here to tell you a couple of upcoming things that are very exciting and happening. We have a virtual screening of a fantastic Sami film from the Indigenous Film, or the Indigenous Film and Arts Festival. That is going to be virtual, so you don't even have to drive over here. You just go to DMNS.org, register, watch it online. Watch that with us, please. We would love to see you there virtually. On April 24th, we have a really amazing program with Lisa Lucero. Dr. Lisa Lucero, she wrote a book called Maya Wisdom and the Culture and the Survival of Our Culture. So it's about the things that the Mayans did that could maybe potentially teach us about how we could save the planet moving forward. Really fascinating talk. She actually grew up here in Colorado. Anybody ever been to Science Lounge? Science Lounge. Yeah, that's what I like to hear. We have another one coming up in July. Tickets are going to go on sale for that soon. So keep an eye out. It's going to be the Sounds of Summer. It's going to be a blast. We're going to have like 4 to 6 bands here. We're just going to blow the top off. It's going to be a lot of fun. Anyways, that is my 2 minutes of material. Thank you so much. I'll come down to the lion's lair. It's a lot worse. I'm kidding. Nobody gets that joke anymore. Anyways, thank you so much for coming to 60 Minutes in Space. This is a wonderful free program that we had the last Wednesday of every month. Usually it's held by Dr. KaChun Yu. This is not Dr. KaChun Yu. This is Naomi Pequette from Peak Nova Solutions. We're honored to have her here tonight. Thank you so much. And please, big round of applause for Naomi.
Well, thank you everyone for coming. My name is Naomi. I am an astronomer and a science educator, so it is my job to take the current space science news and research that's happening and make it not a super technical paper, and fun and accessible to you all. And so I do that through my own company, Peak Nova Solutions, but I used to work here at the Denver Museum of Nature and Science with Space Odyssey. I've taught at the University of Denver, and done stuff, now currently working with UCAR and NCAR on an exhibit that is opening hopefully in May on a topic closely related to some things we're going to talk about tonight. So if you've been to 60 Minutes in Space before, you know our goal is to share some of the most current space science news that is happening. I'm going to flip the script just a little bit, and that there is one topic in particular that's really been catching my attention for last year and this year. And that is our sun. So this is a beautiful set of images from the Solar Dynamics Observatory and NASA mission from just a few days ago. This was the 20th of March. And you can see there's a lot happening on the sun right now. And we've had some current news stories happening in this past month as well. And if you're on social media, follow the news, you might be seeing more and more infographics like this from up in Boulder at the NOAA Space Weather Prediction Center saying, geomagnetic storm arriving, coronal mass ejection, aurora possibly visible, right? These are great catchy headlines. And we had some great events happening like in May. Did anyone go out in May and see the aurora here in Colorado? I shouldn't be raising my hand. I did not. I had a 2-week-old, so no. But my friend Laurel did. This was a picture with her iPhone, right? And these events are happening more. We haven't really heard this kind of activity, especially this far south. And so I wanted to explore why that's happening, what it all means, why this is relevant right now, and then there's a couple of news stories that have come out in the past month that kind of tie this all together as we start to explore this a bit more. So we're going to start with some basics. What are we talking about? The sun. So the sun is a pretty average size star, average temperature, middle of the ground in terms of stars in our cosmos, but it still could have 109 Earths across it and fit 1.3 million Earths in it. So it's still a pretty large object in our solar system. And what's so exciting about it is it's dynamic and it's ever changing. If you've ever come hang out with Dave and Tom over there on the solar telescopes, up on the sky terrace, you'll know if you come back day to day, even sometimes hour to hour, right, that sun is changing. There are new features to see on it. And it's incredibly difficult to be able to understand this, to model it, to predict what's happening. And this is a huge area of research called heliophysics. And my favorite weird term in astronomy, magnetohydrodynamics. There's lots of cool magnetic fields. Don't worry what that means. I just think it's a fun tongue twister. So let's take a look at our sun. You can think of it like an onion. It's got 7 different layers to it, approximately with 7 different zones. So at its center is the core. This is the engine of our sun. This is where hydrogen is being fused into helium, and that's what's producing the energy. It's essentially a nuclear bomb in the middle there. And so we've got a really extreme area of density of 1,000 times of water, 200 billion times the surface pressure of Earth, right? And a lot of intense heat at 15 million degrees Kelvin, which is about 27 million degrees Fahrenheit. But eventually that energy's got to get out, right? We have nice days like today. We're obviously getting energy from the sun, right? We're warming, feeling out. So our next 2 zones are how we're transporting energy out. This next layer is called the radiative zone, right? We're transporting energy via radiation, via light. But this isn't a really efficient process. Those photons have to go through still a very, very dense area of the sun, and they do something that we call a random walk. Is that the photon's emitted, and it tries to go somewhere, and uh-oh, it hits another particle. Okay, so it might scatter, it might try and go over here, and then it goes over here, right? And it's kind of this chaotic walk out if it doesn't get absorbed. So just trying to get out of that area, they only travel about 0.1 millimeters on average before they encounter another particle. And that means it can take up to 200,000 years for a photon to make its way out of that radiative zone. To get all the way out, past the radiative zone, past the convective zone, past the photosphere and the atmosphere, can take upwards of 500,000 years. So the light we're seeing is very old, but it does come out. Next zone is convection. So is the convective zone. We're transporting energy via convection. So think of a pot of boiling water, right? You heat up the water from the bottom. That hot air rises up, or hot water rises up. It cools and sinks back down. Another way to think of it is very relevant to me today. We haven't turned on our air conditioning, right? Which is going to be more hot, the second story of my house or the first story? Second story. It's really toasty up there right now, right? So that hot air rises, cool air sinks. So we're doing the same thing, but now we're playing with, million-degree plasma or so. It's fine. But the area I want to get to is our surface, quote unquote. It's not solid, but we'll call it the surface of the sun, our photosphere. This is the lowest layer down in the sun we can see. And the reason I told you about those other underlayers is so we can see this cool result of convection. Right? We can see this in the photosphere. This is what we call granulation. So if you look at it, then you see kind of an orange peel texture to the sun. And that's because these outer edges are cooler. So this is warm material rising up, cooling off, and sinking back down. Now we've cooled down a lot. We're 10,000 degrees Fahrenheit. Spend a day there. It's fine, right? And the density of our atoms here now are low enough that all of those photons of light that have been trying to get out from the center can finally escape. And that's why we can see this layer. Now, features here are not small, just to give you an idea. We see something called a supergranule, so one of these largest granulation patterns. Those can still be 2 times the diameter of Earth and last 24 hours. These smaller ones typically are more like the size of the state of Texas or larger, and they'll last a couple of hours. But we see that the sun is not static, right? On a regular basis, it's changing. But the big feature we see here, and that's relevant to our stories today, is sunspots. All right? Now, this is more like what you would see if you looked through a solar telescope. It looks like we have a solid surface, right? But this is actually still kind of a cloud of gas. So if you think about a cloud, right, here on Earth, when we see a big cumulonimbus cloud, right, a big thunderhead, it looks like it's got a very distinct solid edge to it, right? Now, if you fly through that cloud in an airplane, you'll know you kind of go through a gradient, right? There's no distinct edge to it. And that's the same thing here with our photosphere. Now, these sunspots are our darker regions that we've got there, and they're darker because they're cooler, okay? But if we took a sunspot and we pulled it off the sun and just had it hanging out, it would still be about the same brightness as a full moon, right? So they're still extremely bright, and they're still extremely hot at about 4,000 degrees Fahrenheit. But these sunspots aren't static either. Just like that granulation, we see sunspot groups develop and form. They rotate across the surface of the sun. They dissipate. And if we look at these, we can actually track the solar activity. Now, we've been observing sunspots for 1,000 years, and some of the largest ones were actually observed on really foggy, hazy days. You could kind of see the sun and see dark spots. Don't do that. Do not look at the sun unless you're with safe solar telescope operators who have safe equipment, right? And they will tell you you can look at the sun. But we've been systematically watching and tracking these sunspots, and we see how they change. So this is, again, a video from the Solar Dynamics Observatory. This was back in 2021 from February 7th to the 21st. And we can see this in amazing detail now, more than we could just looking through fog or even looking through modest-sized solar telescopes here. And if we look at the number of sunspots, if we track them, we can learn about that solar activity. And so really systematically, we've been tracking this since the 1800s, but we have data going back to the 1700s. And this is all data from NOAA's Space Weather Prediction Center, which is here in Colorado. It's up in Boulder. And they're working on trying to kind of get this data calibrated so you can really compare it. But what you're seeing here is the number of sunspots per month versus the year. And one of the things that's very clear is that we have a cycle, right? This is called the sunspot cycle or the solar cycle. And it's about an 11-year cycle. And we have solar maximums and solar minimums. So solar maximums, obviously, we're seeing a lot more sunspots than we do at solar minimum. And so you're more likely to, at any given time, look at the sun and see a sunspot. Now, at maximum, we've seen over 200 sunspots, right? And minimum, we've gone weeks and weeks without anything. But not every cycle is exactly the same. So you can see cycles 5 and 6 here, right? We didn't even crest 100 sunspots maximum per month. And going back even further, there was the Maunder minimum from 1645 to 1715, which is this really prolonged solar minimum. So it's not always exactly 11-year cycle. And then there's cycle 19 here, right? Blew everyone out of the water with its number. So our last solar cycle was pretty meek, pretty mild, not the most exciting to look at. But we are now solidly in this solar cycle 25. And we really deeply want to understand how active that sun is going to be, because this has huge implications of what happens on Earth. So here's solar cycle 25. So here was the peak of our last solar cycle in about 2015. You can see we dipped down really low. COVID, there wasn't anything fun to look at on the sun. Galileo had it good, let me tell you what. Like, well, don't get in house arrest because of the Vatican. Maybe a bad plan. But he at least had a lot of great sunspots to look at, right? COVID, not so much. But we've been slowly ramping up that number of sunspots that we see. And you can see last year, we were at a pretty high number. And here we are in 25, and we're still going up. So what does that mean? What exactly is going to be the maximum, and how much activity are we going to be seeing? So NOAA actually worked with NASA and the International Space Environment Services to do an international panel to try and figure out how active is the next solar cycle going to be. How many sunspots are we going to see? And that's what you're seeing here in red, was this prediction. And so they put together, in 2019, about 50 different predictions to make this one single prediction. But it became very clear just a couple years later that we were going to beat that, right? So this is our monthly observations. Here in blue, here's our old prediction. And so what's just come out recently and from earlier this month, are some new predictions of what this solar cycle is going to look like. And that's what you're seeing in our purple line here, with some uncertainty, because we're never exactly sure. We're not going to say we're going to see exactly 192 sunspots on a given month, right? There's some error there. But what's clear is that this is not our previous solar cycle. We are seeing a lot more solar sunspots. We're seeing a lot more solar activity. And we're probably close to peak. So this is the time we are going to see the greatest impacts. But this cycle will last, we'll probably see these big impacts through 2026, maybe even 2027. We'll still be higher than we were for the entirety of the last solar cycle. So what's causing this? Well, it all has to do with magnetic fields. So if we think about Earth, right? Earth has a pretty simple magnetic field. We've got a North Pole, we've got a South Pole. We see those pretty little loopy magnetic field lines. The sun's not quite like that. It gets a little twisted. And so as the sun is rotating, and it rotates faster at the center than it does at the top, we get points where we have some tangled yarn of magnetic fields. And we get these extra little loops, and that causes our sunspots. So we see a magnetic loop go out, come back in, and we get a nice pair of sunspots. We normally see sunspots in pairs. And these magnetic field lines coming out stop that convection. They stop that hot material rising up, which is why we get a cooler spot. But they're also an indicator for the whole sun's magnetic field. So this is what we call a magnetogram. So we can look at our sunspots. So here's a pair of sunspots. Here's a pair, here's a pair, here's a pair. And so I always have to look at my scale. Black is where that magnetic field's pointing out towards us, and white's where it's pointing in, right? So there's our little loop, okay? And we have these nice magnetic pairs. And what's cool is we can see, if we look at the sun, let's take this nice example here, that in the northern hemisphere, that polarity, so what side sunspot has the magnetic field lines coming out, what side sunspot has them going in, is the same all across the northern hemisphere and opposite in the southern hemisphere during a cycle. But the sun, in addition to getting all twisty, topsy-turvy, also flips its magnetic field. Now, Earth does this every 30,000, or not 30,000, 300,000 years or so, right? We've got a nice, long time between this. But the sun's magnetic field flips in 11 years. And that is our solar cycle. And that is why we look at these sunspots, not only the amount that's happening, but when they're an indicator of when that flip is happening. So if we look at our pairs, right, in northern hemisphere, we've got the black on the right, white on the left, right, left. You can also see lots of sunspots, suddenly not so many. And now we're starting to see more, but we start to see them flip, right, as we come along here. So this was a series of images taken over about 7 years or so, right as we went through that flipping period. So that's an indicator, more than just counting sunspots, that something's happening. And when you have some weird, twisty magnetic field lines, you get more than just sunspots. You start to get flares, prominences, and these beautiful active regions. So here's a full solar cycle from 1996 to 2006. So you can see solar minimum, right? Not a lot happening. As we go on, we see more and more and more activity. So a sunspot's happening on the surface of the sun, that photosphere, but we start to see other things happening. There are other layers out in that atmosphere of the sun, in the corona and other layers of our atmosphere of our sun. So it's the same latitude and longitude, if you will, but at different altitudes, that all of these different phenomena are happening. And we know that solar flares now are more likely to occur during solar maximum, and that the atmosphere, that corona of the sun, is much more visible during this time. You can even kind of see hints of it here. It's not the best image to see. It's kind of puffing out. It's a little bit more visible. And so collectively, we call these areas active regions. But what we want to pay attention to for us here on Earth are solar flares and coronal mass ejections. So here's a great video of a coronal mass ejection from NASA. So solar flare, kind of smaller on the scale, is this kind of what they call a violent event. They last 5 to 10 minutes, and they release a total amount of energy equal to 1 million hydrogen bombs. Not small stuff. Now, our large flares can last for several hours, and they emit enough energy to power the United States for 100,000 years at our current rate of consumption. Near the maximum, we can have a solar flare several times a day. And most of these, no big deal. They're pointing off to the side. They're not heading towards Earth. They're beautiful to look at. Come see the solar telescopes here. And we'll see a major one every few weeks. And we see them a lot in this different view. So now when we're looking at the sun here, we're not looking at our surface. We're looking in what we call hydrogen alpha light, which is allowing us to see further out into the atmosphere of the sun. And at the moment they're emitted, they're about 18 million degrees Fahrenheit. And they emit not only visible light, but X-rays, ultraviolet light and radiation. And that's what we're starting to see towards the end of the video here. Now, if we release an immense amount of material, we call this a coronal mass ejection. So when I say material, these are hot, charged particles. Okay? These are electrons and protons and neutrons, and we're about to see a coronal mass ejection here. Send a bunch of this material out. And that electrical charge can interact with the magnetic field and our atmosphere of Earth and other planets for that matter too. And these are huge, huge events. So this field of trying to predict this, of trying to figure out, hey, when can I go out and see that cool aurora again, is called space weather. Okay? And we know that on a regular basis, the sun is emitting a stream of charged particles, and we call this the solar wind, right? And some of those will interact, which is why it doesn't really matter what year you go to Alaska or Iceland, right? You can see the aurora borealis, or if you're in the southern hemisphere, the aurora australis. And they speed away from the sun at about 1 million miles per hour. But the amount of solar wind we see is directly dependent on this solar activity. So we want to know when the sun is going to be more active to know when we're going to get hit by a huge stream of particles. And we're more likely to see these coronal mass ejections. So this research is going into what are the solar phenomena that cause this stream of particles, what causes these phenomena, right? So that's great that we know we get a coronal mass ejection. Why do we get a coronal mass ejection? And then we look at what is the impact to each area of Earth, from technology to atmospheric effects to seeing those aurora, things like that. And so, like anything in science, we want to quantify this. And SWPC, the Space Weather Prediction Center, has done that by coming out with space weather scales. And so just like we think about tornado or earthquake scales, right? These are on a scale of 1 to 5, 1 being, relatively speaking, mild. That one from a few days ago was a 3, up to our more extreme. And so There are 3 different types of storms and scales that we deal with, and those describe the impacts that they're going to have on Earth. So one that we don't hear a lot about but has a big impact are these radio blackouts. These usually arrive first. This has big impacts on natural disaster response with airlines, air traffic controller being able to talk to flights and whether flights can actually fly or if they get grounded. Radiation, which can have impacts higher up, things like the International Space Station. But generally what you're hearing about are these geomagnetic storms. These are the ones that coronal mass ejections cause. They arrive kind of last usually. And we have, this is really terrible resolution, I'm sorry. I took a screenshot of their PDF. It's beautiful online, I promise. But things like power systems, spacecraft operation, other systems. And they'll tell you how likely it's going to happen. So a G5 storm, 4 per cycle is the average frequency. We're knocking that out of the park. Okay. And to top it off, we've had some pretty darn historic events, like that event in May. This is actually an image of one of the solar flares. It was the largest solar flare from that May event. That I look at the rating was an X 5.8, which is huge, right? And so we see this. We also had a really big storm in October of 2023 that impacted Europe and the UK in particular. That while they're at G5, they're pushing the scale limit to G5 plus. What does it mean when you break a scale? So this past year, NOAA got together again with NASA, the National Weather Service, and some other groups to try and say, hey, this scale is broken. First of all, why? I mean, the 3 scales make sense, right? It makes sense that you're describing impact. But when you're communicating that to the general public, it's really not all that clear. So they want a scale not only that better describes the events like we had in May, which these are both from, but is easier to communicate to the public and is easier to work with their customers because NOAA sends this information out to electrical grid operators, to the FAA, to satellite operations, from GPS to NASA missions and more, and they get space weather predictions. So if you think back to one of our early slides, that's a nice public-facing version with the pretty picture of where the aurora might be. And that is a critical warning system to know how to protect these systems. And so the work has started. They went out, they talked to members of the general public and some of these customers. They got about 500 responses. And so they came together in January, presented at a conference, their results, and the answer is, yeah, we got to come up with a new scale. They could have told us that before they did this, but here we are. And they want to start to implement this. So they're starting the work now. They haven't actually said what the new scale is going to be. That's fun. That's going to start here potentially in the next 2 years. But it's going to take about a decade to completely overhaul the Space Weather Prediction Center and that service, that subscription service that goes out. But it's really exciting work because it's coming from the fact of understanding that now is a time where, first of all, we have a lot of solar activity, but we also have some of the most systems that could possibly be impacted, which we'll talk about here in a second, right? So current work happening right now here in Colorado to update the system, to update how we're notified about this, and we're starting to get the more science to be able to understand when these storms are coming, and that's really great news. So what are these impacts? So here's another view. There's that solar wind we talked about, right? And those charged particles can come along our magnetic field, most of them deflected away. We're in a pretty good spot. We've got a nice magnetic field, we've got a cushy atmosphere. We're in Goldilocks zones just right. But some of those particles do come in, and one of my favorite reasons I love solar activity is we get these beautiful aurora. And so where our magnetic field enters and intersects with our atmosphere, we get a nice little oval, and that's where our aurora appear. And you get some beautiful views like this. This was up in Alaska, I do believe. And those different colors are interacting with different elements here in our atmosphere. So what's important, though, is there's a lot more impact beyond the beautiful images. Go see an aurora if you can. But when that solar wind reaches Earth, it does a few different things. It causes our magnetosphere to contract and then expand after that storm passes. And so this is going to cause some electromagnetic disturbances. When we get a solar flare, we start to shower our upper atmosphere with X-ray radiation and energetic particles and UV radiation. And this can ionize atoms in our upper atmosphere. So what that does, we've got an atom, we now have some freed electrons. Those freed electrons are nice and charged. They really like to build up charge on spacecraft, which have a lot of electronic components to them. And that can actually damage the electronics. So things that we've got going on, some of those like GPS satellites, other satellites are going to be affected. So solar flares, we can radiation harden some for that, that's okay. But with a coronal mass ejection, we're getting a bubble of tens of millions of tons of gas that reach Earth. And those heat up our ionosphere, which is this nice layer in our atmosphere. And that causes our ionosphere to expand. And this can cause friction between it and some satellites that aren't really meant to orbit in the atmosphere. And so we start to see in those low Earth orbit satellites drag, pulling those down. Okay? That's not great. We want those to come there, to stay where they are. And even our International Space Station hanging out in low Earth orbit can start to get dragged down. Now, we've got boosters for this. It's okay, but it's not something that we really want to have happen. Also, when you get this stream of charged particles hitting our nice magnetic field, that magnetic field doesn't stay in the same shape. It's going to distort in response to that. And that distortion of our magnetic field means that that electrical current and those electrons can get accelerated really fast to high speeds. And when those charged particles get to move really fast, now we're not just building up charges on the outside of satellites, they're penetrating deeper in. And that means we're going to damage and potentially permanently disable operations of some satellites. And a big one for this is disruption in communication, right? We have a lot of satellite-based communication now, and cell phone communication can even be disrupted here. But when it gets really bad is when we have those big geomagnetic storms, we can also get disruption to our electrical grid. This was the big one for that October storm, that Halloween storm in the UK, is that you get a bunch of charged particles going along these electric lines. You can blow transformers. You can cause large power outages. This also happened in Quebec in 1994. That caused large portions of Quebec to be without power, 1989. And they lost power for 9 hours. So electrical grid operations, huge subscription to NOAA Space Weather Prediction Center because they can strategically shut down parts of the grid and do a planned blackout instead of losing equipment. But we also want to know if we're going to get these big solar cycles, do we need to invest in the infrastructure like the UK did to harden our grid to be able to avoid some of these problems? We can also see distortion of satellites sent by signals from satellites like GPS. So if you ever, this actually happened to me at a storm in, I want to say like 2012, 2013. I was driving along with my cell phone trying to go to an interview. I was like, I had no idea where I was going. And my GPS signal was nowhere near accurate. This also was a bad cell phone time. 10 years ago, cell phone GPS signal's not quite what it is now, right? And so for us, that's a mild inconvenience. For military operations, for rescue operations, this is critical, and we need to know when that disruption is going to happen. It can also expose astronauts and even passengers in high-altitude flights to larger levels of radiation than we find acceptable. So this can ground flights for hours, potentially, and that can also then cascade effects for days as flights get delayed. So now astronauts themselves have a lifetime limit for radiation, and on a typical day they see about 8 chest x-rays worth. So a large CME could be potentially career ending for them because they hit that lifetime limit. And also they're human beings. We don't want them exposed to that much radiation. So right now, our warning is we see a coronal mass ejection on the sun. That's great. We have a few days' notice, and we can do a little bit of study, and we can get some warning that that's coming. But that's it. So the big push is now to find out what causes those coronal mass ejections, those solar flares, holes in our corona. And if we can predict signs that that might be coming, can we give more notice to these operators in the FAA, their electrical grids, our radio wave disturbance, right, radio communication blackouts to warn them what's happening. And while the May 2024 storm was impressive, right, Aurora as far south as Georgia, that's pretty darn cool, right? It's nothing compared to something like the Carrington event. So this happened in 1859. We had 2 amateur astronomers independently observed an extraordinarily bright solar flare. And Richard Carrington was looking through a safe solar filter because, again, do not look directly at the sun. Okay, cool? Got that message? Awesome. And he thought he had a problem with his solar filter because he saw a spot of light so bright, he thought he had a hole in his filter. So story goes, he went around, he checked it, he looked, he came back, looked, came back, looked again, and then it was gone. Right? So we have 2 different observations of this. About 12 hours later, there was a correspondent for the Rocky Mountain News, which was a newspaper here in Colorado, who was sleeping out in the open air, and they wrote, quote, "A little after midnight, we were awakened by the auroral light so bright that one could easily read common print." That's pretty cool. And as that sky continued to brighten, their party began making breakfast because they thought it was sunrise, right? But the snafu was really in communication. At that time, we were using telegraph. And so telegraphs had these wires that came in and out of buildings, right? Nice wire to conduct electricity. And charged particles overwhelmed the Earth's magnetic field, came down, traveled along those telegraph lines, and actually sparked in multiple places, disrupted that communication. And there's some few reports of small areas of buildings catching fire. Not so good, right? And now for this one, the aurora they could see as far south as Hawaii and the Caribbean. Now we can continue to study this event even though it happened in the 1800s by looking at ice core samples. And they show that the Carrington event was twice as big as any other solar storm in the last 500 years. So what would happen if this happened today? We have a couple days' notice. We are so much more dependent on wireless communication, on our satellite data, on flights internationally, on our electrical grid, right? It's not just telegraph lines now. And if we bust out transformers, this can take years to repair. So we need a good warning system, and we need a deeper understanding of the sun to help us feed those computer models to predict what we're doing. And we're at a critical moment in time to do that. So we study the sun across the world. This is ground-based observations. This is satellite observations. It's NASA, it's JAXA, it's the European Space Agency. It is multi-governmental agencies around the globe studying this, and even have some, studies happening out on Mars. A little Curiosity rover helping us out there, right? And this is providing us more and more data at higher and higher resolutions to help us understand that complex dynamics of the sun, to feed our computer models, to help us understand when these are going to happen, to make better predictions, right? And this fleet of satellites that you're seeing here are all NASA missions, right? So they're strategically placed throughout our entire solar system, from the Parker Solar Probe, which we'll talk about in a second, way out to the Voyager spacecraft, right, on the edge of our heliopause, which is pretty darn cool. So let's talk about two missions that are doing some really awesome stuff to help us study the sun right now. And one is the Parker Solar Probe. This mission is on the 24th of December, so Christmas Eve. It broke a record. It got the closest to the sun that we've ever gotten at 3.8 million miles and was the fastest moving human object ever made, which was pretty darn awesome. So this is a NASA space probe. It was launched in 2018, and its goal is to study the atmosphere, that outer corona of the sun. So we're studying that solar atmosphere. And it became our first mission to fly through the corona in 2021. That's still some pretty extreme temperatures and radiation. So kudos to the engineers who made this probe. And it's collecting measurements and images to help us understand the origin and evolutions of the solar wind, right? So this wind that we see on a regular basis, but also with these solar storms to help us make better space weather predictions. So December 24th, it did its fly through. It was passing by at 430,000 miles per hour, which is pretty darn fast. And on December 26th, it sent back a message to the Johns Hopkins Applied Physics Laboratory in Maryland, who operates it, and said, hey, I'm okay, right? Which is good. That's all we could get. We have to wait for the spacecraft to get into a more optimal position, then it can beam data down. NASA and Applied Physics Laboratory scientists can analyze it and release that. But what's exciting is it's now in its optimal orbit, meaning it's going to keep coming close to the sun. And it did it again just 4 days ago on the 22nd. It did another pass 3.8 million miles. So this is showing the full trajectory, or more or less, of the Parker Solar Probe. You can see its orbit there. That encounter began on March 18th. Nice artist conception, not real data. I want this real data. That'd be awesome, right? Gets very close, and tomorrow that encounter will officially end. We did get the ping back from it and said, hey, I'm okay. I survived. This is what we like to hear from spacecraft. And we'll get that data in a few days. So we'll watch that again. Why not? But this is getting us higher resolution data closer up than we have ever had before about that corona, which is exciting. And while they're waiting for their data to come in, the Johns Hopkins Applied Physics Laboratory and Parker Solar Probe team have another reason to celebrate this week. They were awarded the Robert J. Collier Trophy by the National Aeronautic Association. So this is an annual award that recognizes exceptional achievement in aeronautics and astronautics in America with respect to improving performance, efficiency, and safety of space vehicles. So there were 3 technologies here that they were awarded for. First of all, that heat shield. Holy mackerel, that heat shield can survive up to 2,500 degrees Fahrenheit. And it also is solar powered, which sounds great. You're getting real close to the sun, right? Yeah, give me all that power. But the problem is that you've got to actively cool those solar panels because you're getting so close. So it was the first of its kind to do that. And it's also a fully autonomous spacecraft. It can operate on its own, manage its own flight behavior and orientation for months at a time, which is pretty darn cool. So kudos to this team. Awesome achievement in space flight. And 3 months from now, we're going to do it again. Now, we also launched a brand new mission studying the sun called PUNCH. This went up on a Falcon 9 rocket from SpaceX on March 11th. There were actually 2 missions that were aboard, the PUNCH mission and SphereX, so it's Spectrophotometer for the History of the Universe, Epoch of Reionization, and ICES Explorer, catchy, SphereX, and the Polarimeter to unify the corona and heliosphere, PUNCH. So PUNCH is 4 small satellites. They separated in 2 pairs at 52 and 53 minutes respectively from liftoff, which is what you just saw there. And these 4 satellites will orbit Earth at an altitude of 385 miles. And so the goal of this mission is to basically create a little network to track individual disturbances in the inner heliosphere, so that kind of region closest to the sun. Another cool Colorado connection, these spacecraft were developed by SWIRI, the Southwest Research Institute, along with a few other key players. And they developed these 4 suitcase-sized satellites, and they have imagers that are sensitive to polarized light. So think about your sunglasses, right? If you get polarized sunglasses, you look in a nice lake or water, right? You can see fish, and you can't see fish if you take them off. Polarized light basically is just going a very specific direction, aligned with electromagnetic fields. And this is really helpful because it will actually give us some 3-dimensional data, and it's tied to the types of phenomena that we're looking at. But the field of view of this thing is incredible. The imagers have a view that's anywhere from 1.5 degrees to 45-degree view away from the sun. So we can see anything from that kind of outer atmosphere to nearly the distance of Earth's orbit. So we're monitoring 6 to 185 times the sun's radius, or about out to 80 million miles. And so for the next 2 years, they will take observations every 4 to 32 minutes. So we will understand really what is happening on the sun and how that's impacting our inner solar system with the solar wind. And more importantly, they'll be able to see how dynamic changes in that inner corona propagate outward. So this is an example of what that data will look like. So 3 of the spacecraft have wide field imagers. 1 has a narrow field imager. And those wide field imagers will put together this kind of mosaic of an image looking at that full area, and the narrow image will be much closer. They're both coronagraphs, so they're blocking out the light of that surface of the sun so we can see the atmosphere there. Now, in addition, another Colorado connection, CU Boulder students, 50 of them, through the Space Grant Consortium, designed an X-ray imager that went on all 4 spacecraft. Unfortunately, something happened on launch that failed, so they have to turn that off. But very cool, NASA is still engaging students in a lot of their missions. CU Boulder students had an imager, or had an instrument on the New Horizons mission to Pluto as well. So now we're getting close-up images of the sun from Parker. We've got the Solar Dynamics Observatory. We've got SOHO. We've got a lot of other great imagers. But now we have a comprehensive view, basically, of the entirety of Earth's orbit once this mission is done, of how space weather and space events are impacting Earth. And so much of that is happening right here in Colorado. The Space Weather Prediction Center, as we've mentioned many times, up in Boulder, SWERI, CU Boulder is key, and NCAR, which is operated by the National Science Foundation up in Boulder as well, has observatories on Mauna Kea that are just absolutely phenomenal, helping us to observe the sun in as close to real time as we can. And this is operated by UCAR. They're the same group, but complicated. Anyway, but they have the Mesa Lab, which is a public space as well as a research space. You can go up and visit in Boulder. Beautiful hikes around it. They have exhibitry, and we have just redone their Sun-Earth Connection exhibit. Cross our fingers. Grand opening is supposed to be May 16th. So check out this summer, go up there, see a really cool exhibit, learn about the work that they're doing and the impact of space weather here on Earth. So one last quick story for you all, because it's not just the sun that's active, it's all stars. And so understanding our sun and this really great rich data, as much as I've talked about how frustrating it is, we need more data, it's actually really good data. We can't see other stars in that level of detail. So that can help us inform our studies of other stars. So my friend Meredith McGregor, who used to be up at CU Boulder, is now out at Johns Hopkins, has been studying this star here, Proxima Centauri, our next closest star. It's a red dwarf, small, cool little star. We thought these were great stars to host life. They're small, they're common, they're cool, they're very, very stable for long periods of time. Proxima Centauri has rocky planets around it. But back a couple years ago, during a pretty unprecedented observing run, she observed this star brighten 14,000 times what it normally is in ultraviolet. And so that was this huge stellar flare. And she just went back and released a paper this month looking at about 50 hours of data in the radio waves from the Atacama Large Millimeter Array. And she was able to observe through that over 400 different stellar flares come off of this. And so what she said is basically that this star is so active and these flares are so much more intense than what we have here on Earth, that this could be atmosphere stripping. So this little rocky planet hanging out here like Earth, magnetic field gone, atmosphere potentially gone. So not so great for life hanging out there. So we're thankful for our kind of average sized sun being pretty calm. But those mechanisms of what causes stellar flares, and it was informed by what's happening on the sun and our studies there. So we can continue to study out into the universe, study exoplanets, which is a huge field here, and how those stars impact them as well. So with that, we will open it up to Q&A. Thank you all for joining me on my little journey about space weather. Oh, I don't know if that's on yet. So Austin has a really cool box.
Yes, it's a very, oh yeah, there it is. All right, so this is very soft like a beach ball, so whenever you raise your hand, I'm going to throw it at you, okay? But don't worry, you say your question, then throw it back to me. Can we agree? Yeah. Fantastic.
He's not joking.
I guess can you hear me? Okay.
Yeah.
You mentioned the need to have more warning, more advance notice. What would we do with that information if it's still going to happen and still going to affect the, all the systems you mentioned? What could we do to minimize it?
That's a great question. So what could we do to minimize the impacts there? So one thing we could do, the power grid's a great example, right? It takes an extraordinary amount of time to figure out exactly where this might hit and the impacts that could happen. So we could more strategically shut down parts of the power grids to help prevent some of that. We could prevent flights from being midair when these events occur, right? Where the events, being on a flight when this happens is dangerous for two reasons. One, the radiation exposure, but two, you lose contact with ground control. Okay, and a lot of points too, the only way they know where that flight is by triangulating based on who's talking to it, right? So if you lose that contact, you lose the flight, which could cause mid-air collisions and a lot of other things. So we can do some proactive planning. If there is emergency relief efforts happening, we know we're gonna have a radio blackout, figure out other ways to communicate, coordinate ahead of time, what efforts are gonna be happening when. So things like that. It's also about reframing to be less immediate reactionary and proactive in some of these, to live in this reality. Now, that's not gonna happen this solar cycle. Let's get out. I'm twofold. One, let's get out of it without a big storm, but let's have a big storm. That'd be fun to see the aurora. I don't know. Okay, so my torn astronomer versus human side. Okay. But for the next solar cycle, right, that's where we really want to have those predictions. It's a great question. Yeah?
Okay, you mentioned that Proxima Centauri was a small star.
Relatively, yeah. It's a red dwarf star.
So why would it be more turbulent than our own sun if it's so small?
That's great. That's a great question, right? Why is it? Because we thought these stars, so typically big stars, hot, they live like rock stars, right? They're hot, they're out there, they die young. That's what they do. They live an awesome life, they put on a show. Okay, that was a bad joke, it's fine. These cooler stars, because they burn their fuel more slowly, tend to live longer lives, and we thought they were going to be more quiet. So the fact that this research is only out in the last couple of years, this is a big question mark and a big head scratch, and that's one thing Meredith and her team are trying to figure out is what's happening in there that might be causing this. One thought is that the transfer of energy from the core out is very different, that there might not be a radiative zone, maybe there's just the entire star is a convective zone. And that could be much more efficient at transferring energy out. And that could be messing with the magnetic fields more. But no definitive answers yet. She's making her research off of all this. It's great.
Do we know if anything that we do on Earth, can it affect solar activity?
Ooh, can anything we do on Earth affect solar activity? No, the sun is its own beast. What we can do here on Earth is protect our relationship to the sun. That's weirdly phrased. That came out before my brain processed that one. What we can do is basically minimize the impacts, right? But nothing we do is going to affect the sun. It's a big behemoth. It's a nuclear furnace. We're little. We could throw things at it and it would never know.
I had a question about the Parker
Yeah.
solar probe. So every time it repeats its orbit, is the goal to replicate the same orbit to kind of, try to, just track similar things over time? Or is it going to be doing like a game of chicken where it's getting closer, trying to get closer?
I would love it to play a game of chicken. No, it's pretty stable. It's in its optimal orbit now. So 3.8 million miles is about as close as the spacecraft was designed to be able to get to for that temperature and that radiation. Now, the good news is, unlike something like the moon or a terrestrial planet, right, if you repeated the same orbit, you'd be seeing the same features over and over again. With the sun being so dynamic, we'll see different features every time we do this. And that still is just leagues ahead of anything that we've ever had observation-wise. Great question. Yeah?
You had telecommunication cables in your diagram. I know back in the day they were metallic cables, so they would be subject to some of the same risks as the electrical grid.
Yes.
These days, with them being mostly optical cables, and especially optical cables going up to various licensed radio equipment that's then terrestrially mounted, we're trying to figure out how much of our solar storm damage comes up from the power grid, from the power layer,
Yeah.
versus how much is coming from charged particles hitting those mountaintops or those valleys. Is there data for that? Where do we look? And do we contribute to an RFC as we're trying to get these new weather reports?
Ooh, that's a good question. I'm sure there is information out there. That is not particular research I've dug into. I would suggest starting with the Space Weather Prediction Center because they don't have all the information, but they're really great at linking out to who does. And I know they work with people for that, so I'm sure the studies have been done on that. But that's a great question, right? Because things are so interconnected. In terms of contributing, there's not a huge citizen science effort right now, but depending on what industry you're in, right, there are certainly huge amounts of industries looking at this, and I'm sure there are ways to be involved in that research, and please do, and share what you learn, because that's very cool. Great questions. Yeah.
Question specifically on the solar cycles. I know that just kind of like data science over time, the more that you figure out what you're looking at or what you're trying to look for, the more that you are able to observe and the better that you're able to observe. I'm curious, just knowing that our level of tech keeps going up, we know better, how to track different spots over time. Is there a specific minimal, almost like spot that counts as a spot, or how do we know what we're tracking over time, and is it an increase, is it a decrease, or is it just our level of tech?
So yeah, we're going to see more sunspots now than we ever did, right? So this is one of the big things that NOAA has started doing the past couple of years or so, is trying to calibrate this data, because what we could see in the 1800s with telescopes that are pretty modest, that frankly I could go buy from a telescope store right now, right? That equivalent to what we have now with even ground-based and then certainly space-based observatories. We're going to see much smaller spots, and a spot is a spot. If it's there, we're counting it. And so they work to try and get some of that bias out of it, because otherwise these would look much lower. But the tech certainly is helping us understand more on the number of sunspots. It's that calibration to historic, but there's not like a minimum size. Like if it's a sunspot that's there, we're going to count it. Love it.
Hi, you mentioned that we can continue to study the Carrington effect or event by looking at the ice core. What's in the ice?
So, yeah, someone was going to ask me that. I wrote this note for a lecture 3 years ago when I knew what I was talking about. So, Guy, do you know? Oh man, he's my encyclopedia. So basically, like there's impressions that are left in ice cores because of that magnetic field disruption that happened. The details of that I am very fuzzy on. But I would love to get back to you with an answer, and we can find it after the talk, because now I'm curious, and I don't remember. I apologize.
Got another one
Over here.
Some of those astronauts are in orbit 6 months to a year.
Yeah.
do they have dosimeters to how much, let's say, X-rays and gamma rays and stuff, are they accumulating? And do they have, I think you mentioned a career limiting amount to say they can no longer be astronauts after a certain number of missions. It sounds like during one of these especially high levels of CMEs, coronal mass injections, they might have to avoid even launching missions over to International Space Station.
So they do, their radiation exposure is very, very closely monitored, along with all health aspects of their life while they're up there, right, from vision to physical, just health in general. And so yes, there are dosimeters up there. The good news is there are safe areas on the International Space Station that are more radiation hardened. Even things like just surrounding yourself with water can significantly lower your dose of radiation. That was one of the proposed shielding ideas early on for Mars missions, where you're outside of the magnetic field. And so they can go into these areas, but they need enough warning to know that that's going to happen to shelter in place. Or the other thing is they could use an emergency craft, dock to the space station, and come back to Earth to get further into that magnetic field. So it's about getting that warning in time. So there's ways, and the astronauts certainly have sheltered and been fine. We also don't want them on a spacewalk during that time. So we don't necessarily have to avoid launches. At this point, with the level of solar activity we've seen, we just need to get them to safe places. And so even in May, they were able to just shelter in place, which was great news. Yeah.
What's the proxy they use for magnetic polarity that allows us to take the magnetograms in those maps?
In this historic data, or the
the
old?
Recent ones, the one that was grayscale.
Oh, the grayscale back here somewhere. So that is a specific magnetometer that's on a spacecraft that images it. And so they are just measuring magnetic field across the sun and putting it together in a false image. If that makes sense, it's a visualization of just straight up data of that. Does that answer a little bit? Simple answer, yeah, but there's more to it. But yeah, it's a specifically designed instrument that's measuring it across the sun at multiple points. Yeah. Oh no, it's rich. Uh-oh.
You've done such a wonderful job, Naomi. Don't worry about it. I want to quash a rumor I have seen twice on the internet.
I like it. Let's myth bust.
The CME, the enormous amount of mass that the sun is burping out, it's going to hit us and it's going to change Earth's orbit.
Oh gosh, no.
And the answer is no. I've looked at the amount of mass in a CME. If all of that mass were to hit Earth,
which it won't,
the mass is 1/1,000,000th of 1/1,000,000th of Earth's mass.
Yeah.
So we will not be nudged out of our orbit by any kind of a gravitational thing. It's going to be all the magnetic and electronic stuff that you've been telling us about.
Yeah, no, we're not moving. It takes a pretty big thunk to affect the Earth. It's happened. But yes, you're absolutely right. Thank you for quashing rumors. I love it.
Do we have time for one more?
Sure, let's go with one more. Why not? And then if there's a couple other, I can stick around and just talk to you up front here too.
What's the estimated lifespan of the Parker Solar Probe? And do you know if there are any plans in place to repair or manage it remotely to keep its systems functional for a longer period, a lot like the Voyager 1 in 2024?
Yeah, so the great thing about NASA, right, we designed a minimal lifetime for Parker Solar Probe, and I'm going to keep talking until that number pops into my brain. But there is the potential for mission extension, right? So if the spacecraft is still in good shape, if there's still funding and resources available to continue operating it, they will, right? That's kind of the NASA way. And Johns Hopkins is the same way. I want to say it's like 4 more years, but that number, I'm trying to remember why that's in my head, because I was reading about a couple different mission timelines this morning. Let me find that number for you and get back to you, because it's totally escaping me on what that number is. But it's a handful of years. It's not super long, but given how it's doing, it's going to keep going. I'm not worried about it.
I'm happy to keep throwing the mic at people. two people, if we'd like to keep asking questions, but it is 8:05, so we had our 60 minutes in space, so you're more than welcome to drop out if you want, but
Thank
another
you.
hand for Naomi.
And thank you
Yeah.
everyone for joining us, and come back next month. I'll put in the plug. I don't know who it's KaChun.
It's going to be KaChun next month, so. But thank you, Naomi.
Yeah, it's all good. But yes, if you guys have more questions, feel free to come on up. I'm happy to keep answering questions.